Hello, I'm Matthew Lay, and today we are going to study electric charge. Let's get started. We have some objectives in this lesson. First, we want to understand electric charge and how we measure it. We want to grasp electric charge and how it moves within a circuit, which we call flow. We want to know how to calculate an electric charge given a specific amount of electrons. And when we study electric charge, we are basically studying the works of this gentleman. His name is Charles Coulomb, and he developed Coulombs Law. Coulombs Law is a definition of electrostatic force that opposites attract. Unlike or opposite forces attract one another, and like forces repel one another, which is shown here in this little graphic. So the blue sphere to the left, which is negative in charge, it shows there with the minus sign, is attracted to the red sphere to the right, which is positive in charge. But if those charges are the same, like it shows here in the bottom, those charges repel one another. Units, SI units. SI stands for System International. Most people just call that the metric system. All of our electrical measurements that we are going to be talking about in this course are going to be SI or metric units. All electrical measurements are SI or metric units. The System International unit for electric charge was named after Coulomb, so a unit of charge is called a Coulomb. So let's talk about this Coulomb unit. A Coulomb is nothing more than just a collection of electrons. Now, in the previous exercise, we studied the atom, and we know that the atom is made up of protons and neutrons in the nucleus, and it's made up of electrons, or the orbitals around the outside. Those are the three components in an atom. And we are talking about a Coulomb as an electric charge of a collection of these electrons. In this demonstration, I'm going to use this depiction of a sack to denote a quantity of electrons to the amount of 1 Coulomb. Coulomb is represented by the letter Q in math equations. So we are going to do a couple simple math equations today. We're going to use the letter Q to represent them. But the unit itself that we just discussed is a Coulomb. It is abbreviated by the letter C. So this is something in the study of electricity that students will have to get used to. For every quantity, we're actually going to have two letters. One is going to be the letter that it is represented by in formulas, and the other is going to be the units. And it's a way to denote the units from the quantity that the units are describing. Okay, so for a Coulomb, we have Q that we're going to use in math equations, and the letter C to denote the actual units of measure. So let's look a little bit further at this Coulomb unit. Coulomb, as we said, is represented by the letter Q in equations. 1 Coulomb is that amount of electrons. Now, if I put that in engineering notation, as I said earlier, I'm going to use this sack to represent 1 Coulomb. So anytime you see this sack in future slides, I'm talking about that many electrons. So let's see what that is in engineering notation. That is 6 exa 242 peta electrons. Okay, when we have to fathom those in our head, it gets a little bit unwieldy. So it's easier, for me at least, to denote this in scientific notation. So in scientific notation, Q is represented, or the amount of charge that we have, which is represented by the letter Q, is going to be 6.242 times 10 to the 18th power. Remember, 10 to the 18th is just 1 with 18 zeros behind it multiplied by 6.242. So that is, again, a way of denoting this extremely large number. Let's look at how this is actually useful in our electrical study. Now, what I have here is a depiction of a flashlight, and I've broken it down to its insides. So most students will recognize the C or D cell batteries that I'm showing there, and then I have a light bulb here, and these two batteries are touching each other, so they're electrically connected, and then this light bulb is touching the very top there, much like it would in a kind of an old-fashioned light bulb. Of course, I am depicting an old-fashioned light bulb with a regular incandescent bulb here. Most are now LED and have some electronics involved in converting the direct current power from the batteries to a very low source needed for the LED. And then this over here, if you're not familiar with this, is called a knife switch. It is a very, very old depiction of back 100 years ago when they first built electrical switches. They made knife switches, and this is basically just a hinged piece of copper that this is the pivot of the hinge, and the red here is denoting a insulative property that's on the metal, so if you touch it, you're not going to have electricity flow through you. And you would move this knife switch down till it came in contact with a little prong here that it would touch, and it would allow the lower screw terminal here to be connected to the upper screw terminal. Currently, the switch is open, meaning there is no path for electricity to flow. That's one thing that students need to get used to, is an open switch does not allow something to pass through it, where a closed switch does. Now, if you think about a door in a classroom, and to get into the classroom, you have to open the door to be able to go through it, and you close the door to stop any flow through the door. Well, electricity in our case is going to be the opposite of that. So a closed switch allows electricity to flow, and an open switch does not. So here I have two batteries, and they have electrical charge. And you might have even said this in talking about a battery. You can say this battery has charge, or if it is what we termed a dead battery, you'd say it doesn't have charge. And what you're saying is it has a certain amount of Coulomb capacity, or electrical charge built up inside of it that you can use when you put it in some sort of device. So what I'm depicting here with these sacks is that these batteries are charged up, good to go, and all we need is a path for electricity to flow for our flashlight to actually illuminate. So each one of those sacks, like I said earlier, is going to be 1 Coulomb of charge. Of course, this battery would have many, many sacks of charge inside of it. I'm just doing a simple demonstration here. And since that switch is open, we don't have any path for the charge to flow through the light bulb and for the light bulb to glow. So now we're going to go to the other state. Our flashlight only has two states. It's either going to be on or off. The switch is either going to be open or closed. So the switch is now closed. And you saw I brought the knife switch down, and now the lower screw terminal is connected to the upper screw terminal, and I have wires going here, giving us a complete path around around this electrical circuit. The positive terminal of the battery is the top. Of course, the picture that I have here also shows the positive terminal. But when you're putting batteries into a flashlight, like just a typical standard flashlight that has them end to end, this is how they would be installed. And the part that has the dimple on the top is the positive side, and of course the flat side on the bottom is the negative side. So we have different charges on opposite ends of the battery. And we know that these batteries have coulombs of charge in it, And when we have a completed path, what happens is this Coulomb of electrons, which is negative in charge, is going to be attracted to the positive side, because we know from the study from Charles Coulomb that unlike or opposite charges are attracted to one another. So this quantity of negative charge is going to actually be attracted through the wire to this positive charge on the top of the battery. So this grouping will actually move down the wire towards the positive terminal of the battery. And I have a little animation here. So you see that these are moving towards the positive side of the battery, and it's going through this closed knife switch. And of course my light bulb is now glowing because I have electricity going through it. And an incandescent light bulb, when it has electricity going through a very thin wire called a filament, it glows. And so that's where we get our light from our incandescent light bulb. So these groups of electrons are going to move from the negative side to the positive side of the source. And when we study electricity, all we're really studying is the movement of electrons within a completed circuit. And the term electricity literally comes from the word electron, because it is this phenomenon that electrons will move, an atom will freely give up its electrons and move to the next atom to allow electricity to flow. Okay, let's get into some calculations here. So if we have 1 Coulomb, that equals 6.242 times 10 to the 18th power. And if given a set of electrons that is not that exact quantity, so in this case, if I'm giving a set of electrons of 1.2484 times 10 to the 18th, we want to calculate how many coulombs that is. Well, all we have to do is take the given quantity and divide it by the known quantity for 1 Coulomb, 6.242, and that gives us that is just 0.2 coulombs of charge. Okay. Let's continue on with some calculations. If I'm given a Coulomb now, and so we want to go the opposite way. If I'm giving a Coulomb quantity of 2.2 coulombs, we want to calculate how many electrons that is. We're just going to take the 2.2 coulombs times the known quantity of 6.242 times 10 to the 18th number of electrons per coulomb, and that will give us the number of total electrons in 2.2 coulombs. And we wind up with a result of 13.7324 times 10 to the 18th electrons. Okay, let's review. What is electrical charge and how it is used? So a good way to review here is maybe to pause the video and try to answer this question yourself before I actually answer it. So I'll give you just a second to do that. Okay, so electrical charge is nothing more than a collection of electrons, and we term that collection a coulomb. A coulomb is 6.242 times 10 to the 18th electrons. And we're going to use the letter Q to denote charge, and that charge is measured in coulombs, which we abbreviate with the letter C. Okay, groupings of electrons or coulombs move in which direction in an electrical circuit? Again, if you want to pause, answer for yourself, I'll give you just a moment. Okay, electrons, which are negative in charge, are attracted to their opposite, which is the positive. So the groupings of electrons or coulombs will move to the positive side of the source. In our previous example, it was the battery, but it could be a power supply as well. How many electrons are in 2 coulombs? So again, pause the video, calculate that out, and come back. So if we take 2 and we multiply it times 6.242 times 10 to the 18th electrons, we will get how many electrons there are in 2 coulombs. It is 12.284 times 10 to the 18th electrons. So this concludes our study of electrical charge. I hope that was helpful. We shall see you in the next lesson.